In Chapter 19, we're going to be discussing waves and oscillating motion or vibrating motion. This might be of particular interest to those of you that are planning to study sonography, since that's the use of sound waves. All waves fall into one of two categories. We have mechanical waves, when we talk about mechanical waves, we're talking about waves that require matter. Mechanical waves require, and I think this marker is done. Grab a different one. Mechanical waves require a medium. A medium is something that the wave travels through. It might be water if we're talking about water waves. It might be air if we're talking about a sound wave. It might be a slinky or a piece of rope. There's all kinds of things that waves will travel through. But mechanical waves require that matter because it's matter that's actually doing the vibrating. Sound is a mechanical wave. Sound can travel through air, it can travel through water, it can travel through a steel rod, but a sound wave won't travel through a vacuum. The other type of waves are electromagnetic. Electromagnetic waves do not require a medium. They can travel through a medium, but they can travel through vacuums. Our best example of an electromagnetic wave is light. Light from the sun travels through the vacuum of empty space, but it also will travel through water or a pane of glass, so it can travel through a medium. Okay, in this chapter, we're not going to really discuss electromagnetic waves. We're going to come back to those when we study light, but we are going to talk about mechanical waves and what are all the different properties of mechanical waves. However, before we actually talk about waves, let's talk about a pendulum. A pendulum is interesting because it exhibits something called simple harmonic motion. A pendulum is simply a mass on the end of a string. If we have a string, we put a weight on it. There it is. The string has some length I'll call L. This mass here has some mass I'll call M. What I find is if I pull it up here and I let go of it, it's going to move down because of the force of gravity that's acting on it. When I raise it up here, it's got gravitational potential energy. However, if I haven't let go of it, if it's stationary, if I'm just holding it there, its kinetic energy will be 0. So this will be a maximum value because we're not going to raise it higher than that. But the kinetic energy is going to be 0. This is going to remind us of our discussion of conservation of mechanical energy. It will swing until it reaches here. Right here, the gravitational potential energy is a minimum, but the kinetic energy is a maximum. it will be moving fastest right there. Remember, kinetic energy depends on speed squared, 1/2 mv squared. So at its fastest point, the kinetic energy is greatest. It will keep going up until all that kinetic energy is turned back into gravitational potential energy. And then it will just repeat and repeat and repeat. A period of a pendulum is the time it takes to go from here all the way to here and all the way back. So one complete cycle. If you started in the middle, you'd have to go all the way to here and back, all the way to here and back. Okay. This period for a pendulum is so consistent that for many, many years, most clocks were based on pendulums. And if you still might have a parent or grandparent that has a grandfather clock, a pendulum is used to help it keep time. Now, we have more sophisticated things now. They use vibrations and quartz atoms and all kinds of things, but pendulums were where it started. So we know period is a time for a complete cycle. It's interesting that the only thing the period depends on is how long is the string, and what is the acceleration due to gravity. It doesn't depend on a lot of things that you might think would matter. Doesn't depend on the mass. How heavy the pendulum is does not affect the period. That might make you think a little bit about gravity, though. Mass doesn't affect your acceleration due to gravity, and of course this is caused by gravity, so mass doesn't affect the acceleration of your pendulum. It also does not depend on amplitude, and amplitude is how far over this way. Usually we measure in angles. How many degrees this way, how many degrees that way. Those will be the same number, but the period of the pendulum does not depend on how far you pull it out and let it go. It depends on how long the string is and how large the acceleration due to gravity is. If you have a longer string, the result will be a larger or a longer, let's go with longer, period. If you have a larger acceleration due to gravity, that will give us a shorter period. Increasing the value of G shortens a period, or decreasing the value of G, like if we go to the moon, will lengthen the period. So the same 1 meter pendulum on Earth, which has a period of about 1.4 seconds, will actually have a longer period if we take it to the moon. All right, so this is wave-like behavior, but it's not actually a wave. So let's look at waves. If you took pre-cal in high school, you probably studied trig functions, and you probably saw the sine and cosine waves. Sine and cosine waves look just like this. They give us an excellent picture. It's a representation of what most waves look like. I say most waves, actually that's not true. What many waves look like. It's what we think of when we think of waves. This picture helps us define a bunch of terms. So these high points are called crests. These low points are called troughs. The length of a wave, it's called a wavelength. is measured from crest to crest. So I can go from here to here. We'll talk about this symbol in just a minute. Or if I want to, I can run an equilibrium line down the middle. I could start here, all the way down, all the way. That's one complete cycle. It really doesn't matter. The wavelength is the length of one complete cycle. You can go crest to crest. If you go equilibrium, you'll need one bump that points down and you'll need a second bump that points up to get a full cycle. Or you could go from trough to trough. There's a trough, there's a trough. That's the wavelength. The symbol for a wavelength is a Greek letter. It's a lambda. And sometimes kids struggle. It looks a little bit like an upside down Y, but it's part of our Greek alphabet. We measure the wavelength in meters because it is a length, and it's just the length of a complete cycle. One cycle or one repetition. If it starts repeating, you'll notice if we start here and go all the way to here, well then it repeats. Or if I start here and go all the way to here, well after that it repeats. So if it starts to repeat, you're starting a new wavelength. The other thing we need to talk about on this picture is the amplitude. And that is the distance. Again, since it's a distance, we're going to measure it in meters. Most of the time, we might measure amplitude in centimeters or millimeters, but our SI unit is meters. And it is this. It's the distance from equilibrium to a crest, or the distance from equilibrium to a trough, or from that midline. So we say it's the distance from the midpoint to a crest or trough. I've also heard it being described as 1/2 the distance between a crest and a trough. So if you look at this whole distance from here to here, the amplitude would be 1/2 of that distance. But it tells you how far up and down below equilibrium that wave is vibrating. Some more words that go along with all of this. Frequency is the number of oscillations. That's one word. Or complete cycles. Or crests. There's a lot of ways you could count this per second. If you were looking at a picture of a wave and you were counting the frequency, you might start a stopwatch and say, how many times does this wave go up and down, up and down, up and down each second? It might be easier to time it for 10 seconds, but if you time it for 10 seconds and you see that in 10 seconds it makes this trip 50 times, well, 50 cycles in 10 seconds is 5 cycles per second. That would be our frequency. We measure frequency in a new unit. We measure in something called hertz. The symbol for a hertz is an H followed by a Z. This is really closely related to the idea of the period. Remember the period, which the symbol for a period is a capital T as in time, is the time for one cycle. If you think about these are reciprocals. Frequency tells us the number of oscillations per second. Period tells us the number of seconds per oscillation. So we usually say that they are reciprocals. The frequency is 1 over the period, and the period is 1 over the frequency. This is the number of seconds for a complete cycle, and this is the number of complete cycles per second. Now suppose you have a row, you can even have a whip if you want it, and you send one pulse through it. That's a single pulse, and we've seen lots of examples of a single pulse. What actually is that pulse transfer? Well, what we find is a wave pulse, whether it's single or whether it's a bunch of them, transfers energy. After the pulse has traveled through this, the rope still hasn't really moved. It doesn't transfer matter from one place to another. It transfers energy from one place to another. Basically, when we're talking about transferring energy by mechanical means, there's two ways. One is with particle model. If I throw a baseball, that's a particle model, and that transfers matter, the baseball, and energy. If I throw a baseball and hit my dining room window, obviously the baseball had energy, and I transferred the energy from my throw to my dining room window. Waves also transfer energy, but they do it without actually transferring the matter. The energy travels through the matter, and the matter vibrates back and forth about equilibrium, but it doesn't actually go from one place to another. When I talk, if this was a classroom and I was talking, you would all hear me talking, and that's because when I talk, I vibrate air molecules in the back of my throat. Those air molecules vibrate other air molecules. The air molecules that you actually hear are the ones inside your ear. They're not the same ones inside my throat. So I don't transfer matter, I just transfer the energy that I use to speak. Now, if we look at a continuous wave, we typically think of looking like this. We want to let this wave travel this way. That's the direction of the velocity. But the actual matter, this point right here, is traveling up and down. These are called transverse waves. Transverse waves occur when the matter that's oscillating is vibrating perpendicular to the wave travel. So the travel of the wave in this case is to the right, but the motion of the matter is up and down. So the matter vibrates perpendicular to the direction of the wave travel. You've seen that with surface waves on the top of water. The water will be going up and down, but the wave might be traveling that direction. The other type of wave is longitudinal. Now, longitudinal are harder to draw, and I certainly can't draw a longitudinal wave in a rope, but I can draw a longitudinal wave in a slinky. If I have a slinky, it looks something like this. I have places where I've sent this pulse right here, and you can see they're bunched up, and then they're bunched up right here, bunched up right here. Those are called compressions. This is a longitudinal wave. And in a longitudinal wave, the matter vibrates back and forth. Parallel to the wave travel. In other words, this particular coil of the slinky is traveling this way and back. Pick any coil and it's oscillating back and forth from an equilibrium point. This is compressions, where they're pressed up closer together. And the distance between a compression to another compression is the wavelength. So instead of having crests and troughs, we now have compressions, and we have places where they're spaced farther apart, where they're spaced farther apart here in the middle. Those are called rarefications. So we have compressions where they're bunched up close. We have rarefications where they're spread further apart. Sound is a longitudinal wave. If I were to draw a sound wave, it would look like this. A compression, all the molecules would be close together. There's a compression. And then in between, we'd have these rarefications where there were much fewer molecules. That's what a sound wave looks like. You have compressions, you have rarefications. The distance from one compression to another, that's a wavelength. Now that's a picture of a sound wave traveling through air, but it's really very, very similar whether it travels through water or it travels through a steel rod. There will be places where the molecules are closer together and places where the molecules are spread out. It will travel through liquid, air, gas, all kinds of things, solids, if they're elastic and can vibrate back and forth from their original position. One place where you see both types of waves are earthquakes. Earthquakes have what they call P waves. P waves are their push-pull waves. P waves are longitudinal. And earthquakes also have something called S waves. And S waves vibrate back and forth more slowly. So if you were looking at the ground, you really couldn't see the push-pull waves of the longitudinal waves, which tend to look like this, traveling towards. But you'd also see across the ground a slower S wave. So the P waves will get there first, okay, before the S waves. That's one of the places, one of the methods that geologists and people who study seismology and earthquakes can actually determine where the earthquake originated. All right, let's talk about wave speed. The first thing I want you to know about wave speed is the source of the wave, the thing that's vibrating, does not determine the wave speed. How fast a wave travels really only depends on one thing. It depends on the medium. When I stand here and talk, there's a lot of things about the sound wave I can control. I can control how loud I speak, which is amplitude. I could shout at you, or I could whisper. I can also control the frequency of this sound. I can decide whether I'm going to talk way up here in a high annoying voice, way down here in a low voice. But the thing I cannot control is the speed of the sound. Sound will travel at about 340 meters per second in air. I don't have anything to do with that. It'll travel about 1,500 meters per second in water. How fast a wave travels depends on the medium. We do know when we talk about speed in general, that speed is equal to distance over some time period. If we're talking about wave speed, that would become a wavelength divided by the period. They actually don't usually say wave speed is wavelength divided by the period. We know that the period is the 1 over the period is the frequency, that frequency and periods are reciprocals. So we usually see it written that wave speed equals frequency. Remember, 1 over the period is the frequency times the wavelength. Or V equals F lambda. There's really only like 2 important formulas for waves, and that's probably the most important. The wave speed is equal to the frequency times the lambda. So if you cannot change the frequency, if you cannot change the wave speed because you're talking in air, if I increase my frequency by talking way up here, I'm going to decrease my wavelength because that wave speed stays the same. So we can look at how that behaves. Let's just think about what normally happens. When a wave travels into a new medium, the wave speed changes. The frequency does not change. Think about this. Suppose that you had a sound wave, and the sound wave had a frequency like this. So it's hitting, I don't know, a piece of metal. And it's standing here and it's hitting bam, 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 bam as it goes into this. Let's make it a bigger piece of metal. Let's make it a big piece of metal. Okay. The frequency inside this metal, if it travels through this metal, is not going to change because the frequency that it's getting hit is the same. That depends on what's causing the sound. However, I know its speed is going to change. In fact, its speed is going to change and these wavefronts are going to travel so much faster. I'll make it even bigger. That if V increases, what we notice is so do the wavelength. The distance between these crests is now much bigger. That makes perfect sense. Let's look at the formula. If my formula is V equals F lambda, and I tell you that this does not change, then I turn right around and say, oh, but the speed is faster. If this increases, then this has to increase. If I tell you that I'm changing mediums and the velocity is going to increase, but the frequency is going to stay the same, then the wavelength will also have to increase. If I change mediums and the wave travels into something where it travels more slowly, if this decreases, this must also decrease because the frequency of the wave doesn't depend on the medium. The frequency of the wave depends on the source, the thing that's generating the wave. How is it the actual vibrations of the source? Now, we can change that slightly and say, in the same medium, not two different mediums, all waves travel at the same speed. So if I don't change mediums, all the waves are going to travel at the exact same speed. But if I tell you that I have two waves, wave 1 has frequency F, and wave 2 has frequency that's twice as big, 2F. What do I know about the wavelengths? Well, let's look at wave 1. I know that V is equal to frequency times wavelength. And for wave 2, I know that V is equal to frequency, but this time my frequency is 2F. But stop and think. My speed cannot change. We're in the same, if I have two waves traveling through the same medium, they're going the same speed. If this number still has to equal V, then this wavelength must be half. If the speed does not change, if I double F, I have to half the wavelength. If I half F, I'll have to double the wavelength because I know this product still has to come out to be V because the speed doesn't change. Okay, it's not possible for two baseballs to occupy the exact same space when you throw two baseballs, but you can have two waves that actually occupy the exact same space. In fact, if I have a situation where I have a wave pulse going like this, and somebody else has the other end of the rope, and they send a wave pulse traveling like this, when those two pulses meet, I can momentarily get a wave that looks like this. And then I get a wave that looks like this again. This wave will continue right on through, and this wave will continue right on through. But while they're occupying the same part of that rope, they add together. This adding together of two different waves is called superposition. If this wave had been down like this, when they added together, it would have looked like that. Afterwards, the one that went down would carry on like that. When they add together and we get an increase in amplitude, we call that constructive interference. If they add together and we get a decrease, this is a complete decrease in amplitude, we call that destructive interference. Now, if we have identical waves that are in phase. In phase happens when you have two waves that have the same wavelength and they're at the same point in their cycle at the same time. So for example, if I have a wave that looks like this, and I have another wave that has its peaks and lows at the same time. Not perfect drawing, but when I get done, those two waves are going to give me constructive interference. If they're exactly half of the cycle out of phase, one half cycle, or if we're doing some trigonometry for 180 degrees out of phase, that means my highs and lows, instead of my highs lining up with my highs, it means my highs are lining up with my lows. And this looks like this. That adds together to give me total destructive interference. They completely cancel each other out. Now, one of the results of wave interference is a phenomenon called standing waves. And if you've ever played with a jump rope, or a slinky, you've probably made some standing waves. Suppose I consider a string that's fixed here, whether you're holding it or it's tied to a guitar and it's plucked or something. When you send a wave like this, there's a wave pulse. When it hits this rigid bar, it actually reflects back like this. That's a standing wave, but that's not the only standing wave you could make. That's what you typically would see, say, if you plucked a guitar string. You also, though, can get standing waves that draw an equilibrium line this time that looks something like this with the same thing. It goes like this, comes back, this, comes back. This is actually a complete wavelength because it's got a minimum and a maximum, or a maximum. If you only have one bump, that's actually half of a wavelength from here to here. If you shake it faster, let's suppose you and your friend are doing it and you shake it even faster, you can get a wavelength that does something like this. So let me try that again. Let's draw that equilibrium line where you actually get 1, 2, 3 bumps. It looks something like this. There's the wave, and there's it reflecting on the way back. Let's smooth that one out a little bit. That would actually be 1 1/2 wavelengths because it's got 3 bumps. These are examples of standing waves. If they are in the same string each time, we know that the wave will travel at the same speed in this string each time. So if we think of V equal F lambda, well, in this case, the wavelength we see is only 1/2 of a wavelength. We can see that if I want F lambda to equal V, that this would have a frequency that's twice as big as this frequency. I said that exactly wrong. Let's not even go there. These are what standing waves look like. As the wavelength gets smaller, the frequency gets higher. So this is, as lambda decreases, that's our wavelength. Frequency increases. Remember, V equals F lambda. If this is not changing, as this number gets smaller, this frequency is getting smaller, this wavelength is getting smaller, this frequency has to get larger. Or if the wavelength is getting longer, the frequency would have to get smaller. All right, the last idea, no, I don't think this is the last idea, but the next thing we want to talk about is the Doppler effect. You've probably heard of the Doppler effect. The Doppler effect is the apparent shift in frequency when a wave source, and I'm going to talk about sound waves because that's easier for right now, and a listener are in relative motion. What does relative motion mean? Well, they're not standing still relative to each other. Either the source of the sound is moving toward or away from the listener, or the listener could be moving toward or away from the source of the sound. Either way, it's going to produce the same exact results. Now, it's easy to see what happens. We've all seen this. We are parked and we hear a train whistle, and as that train whistle is coming towards us, the pitch sounds up here, but then as that train soars, you get this, it sounds lower when it moves away. Why does it sound higher frequency when it's coming towards us and a lower frequency as it moves away? Well, picture a sound source that's stationary. The source of sound is stationary. It sends out crests. These are like ripples in a pond in every direction. That's a sound wave sending out sound. Really, this should be three-dimensional, but we can only draw it two-dimensional. So there it is. But what if instead of being stationary, it's moving? We'll let it move towards the right. Well, if it's moving, let's say it started over here, but it moves over this way. Let's look at what's happening. When it's over here, here's that first crest. But that second crest is centered from when it was further back. And that third crest, its center of it is even farther back. Remember, this should be at the center of that circle. So now let's put some listeners in the thing. If you're over here and you're listening, this little person, the wave frequencies, these crests that reach him, are much closer together. He hears a higher frequency. But if this listener's back here, and he's listening, these crests are farther away, farther apart. He hears a lower frequency than the original sound. The only way to hear the same frequency as the source is for the source and the listener to be stationary or to be moving together. If there's no relative motion, it'll be the same. The other possibility is that the source stands still and the listener runs to it. But if the listener's running to this, look at this. He's going to hear these faster. It's like running into the rain. He's going to run into this one, bam, 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 bam. He'll hear a higher frequency if he moves towards the source. Just exactly the same as if the source is moving towards him. If, on the other hand, he runs away from this source, let's suppose he starts running this way, it takes longer for each wavefront to hit him, and he'll hear a lower force. So, if they're moving toward one another, doesn't matter whether the listener's moving or the source is moving, they hear a higher frequency. If they're moving away from each other, whether or not the source is moving away or the listener's moving away, the listener will hear a lower frequency, even though the actual frequency emitted by the source didn't really change. All right, the very last topic, our last slide here, is about a couple of different types of waves. The first one's called a bow wave. And a bow wave is a two-dimensional wave on the surface of a fluid. Fluids can actually be liquids or gases. They both have fluid motion, but it's easier to picture a fluid. The simplest case is to think of a boat. If you have a boat moving like this, you've probably all seen, I don't have to draw the motor, but you've all seen the wake generated by the boat. It looks like a V-shaped wave moving out. These are caused when the boat travels faster than the waves in water. If your boat was actually going slower than the speed of the waves in the water, you won't generate a wake. The faster your boat travels compared to the speed of the waves in the water, the more obvious the bow wave was going to be, this V-shaped wave. Now, really similar to that, but slightly different, are shock waves. Shock waves are 3D waves. Okay? We tend to think of high-speed aircraft causing shock waves. They don't let high-speed aircraft travel over ground and over populated areas anymore, so you guys may not have ever heard shock waves or sonic booms. But I can remember being in school and all of a sudden you'd hear this loud boom overhead, and it was a shock wave. What's going on with a shock wave? Well, in shock waves, basically, the aircraft travels faster than sound. Or faster than any wave. But the waves we most often think of traveling through air are sound waves. Okay, we think of them, quote, breaking the sound barrier. We know that sound waves travel about 340 meters per second through the air. So if you have an aircraft that's traveling faster than 340 meters per second, he generates a very, very similar wave. I don't know what the airplane looks like. There's my high-speed airplane traveling along. Only instead of just being V-shaped, it's cone-shaped. It's a three-dimensional cone. Okay. As long as that three-dimensional cone is up in the air, you won't actually hear a sonic boom. But if that reaches the ground, which it will eventually, when that sonic wave, when that shock wave hits the ground, you hear a sonic boom. Sort of a teeny tiny example of a sonic boom is the noise that makes when you crack a whip. If you crack a whip, you hear that pop at the end. That's because the whip is actually traveling faster than the speed of sound. It's not because there's a little microphone on the end of a whip that sends out a crackling noise. It's caused by a little teeny tiny shock wave, because the wave traveling through the whip is faster than that 340 meters per second that sound travels through air. Okay. We're going to talk a lot more about sound in chapter 20, but this gives you a general rule for how things work with waves and what all the parts, what's the amplitude, what's the wavelength, what's the frequency. So you want to know all of those terms. Okay, that's it for this chapter.